How do you describe distance? With a number, obviously, length. But what about describing distance in relation to a coordinate grid, like on a map? Well, then you need two numbers, the lengths along the grid, as well as a formula relating those lengths to your distance. Now, what about if your grid is skewed? Well, then you need to specify a third number for your description, the angle of the skew, and then modify your formula. Let's extend this by asking, what if your grid is three-dimensional? Then you have not only three grid lengths, but also three angles that can be skewed independently. And so you arrive at 6 possible numbers to describe distance. Now, let's push it even further by asking, what if your grid isn't three-dimensional, but rather four-dimensional, with a slightly more abstract formula for distance defined on it? Well, then you need 10 numbers. And it's these 10 numbers that are so crucial for describing our spatio-temporal reality. This is Dialect with the Spacetime Metric. Consider two nearby locations on a map. How can we describe the distance between them? We can start by expressing such a distance in terms of the map coordinates, dx squared plus dy squared. But this won't yield the true distance between those locations, because for a map of something like the Earth, where a curved surface has been projected onto a flat one, an interval dx or dy here on the map doesn't represent the same distance as an interval dx or dy elsewhere on the map. Moreover, the true angle between dx and dy may not be 90 degrees. To calculate the actual distance represented by this coordinate distance on the map, you need a metric, or more specifically, a metric tensor. Essentially a sophisticated bar scale, the metric tensor tells us the true surface distances along our coordinate intervals, and the true surface angles between our coordinate axes for every small patch of our map, with the size of these patches going to 0 in their infinitesimal limit. Since a surface can be mapped in many different ways, different maps will require different metrics. This Robinson projection, for instance, preserves neither lengths, areas, nor angles, and so requires 3 distinct numbers at each patch to describe Earth's geometry. The metric tensor thus relates the geometry of a map to the geometry of a surface being depicted by that map. In our prior videos, we demonstrated this visually, showing how, by first cutting a map into many small pieces, instructions from the metric tensor could be used to resize those pieces in order to fit them to a curved surface. But now, let's consider a different type of map, a spacetime map. Instead of 2 nearby locations, consider 2 nearby spacetime events. Can we describe a notion of distance between them? There are 2 answers to this question, the special relativity answer and the general relativity answer. Special relativity says yes, we can, that any two points in space and time can be related via a single number, known as their space-time separation interval. We write this special distance as a Pythagorean relation between the dt squared and the dx squared. Only now we swap the plus sign for a minus 1. It's no longer our intuitive notion of distance, but it shares some common features with physical distance. Namely, that of being an invariant real quantity. But only so long as we're sticking to inertial frames of reference and local systems. But general relativity trades in both non-inertial frames of reference and in global systems. So this answer gets turned on its head. And we find that, if we try to describe the space-time distance between two nearby world events on an observer's space-time map, via expressing it through the coordinates dt squared minus dx squared, we will run into the same problem we had with describing physical distance on a map of the Earth. That is, an interval dx or dt here on the diagram may not represent the same space-time distance as an interval dx or dt elsewhere on the diagram. Moreover, the true space-time angle between dx and dt may not be an orthogonal one. This is because the geometry of our space-time map, which is flat, doesn't match up with the geometry of the surface that our map is depicting. But let's back up a minute. What surface exactly are we depicting with a space-time diagram? You might think a space-time map is a map of, well, space and time. In fact, we said as much in our last video. Making a map of space and time. But this is rather imprecise. It's like calling a map of the Earth a map of latitude and longitude. Indeed, a space-time diagram is not really a map of space and time at all, but rather a map of world events, which are merely ordered via space and time. How this ordering occurs is observer-dependent, and so each space-time map belongs to a particular observer or network of observers who, based off of light signals transmitted throughout the universe, assign a quadruplet of coordinates, 3 for space and 1 for time, to each world event which transpires. Since in making this projection, the observer assumes that time and space are everywhere independent dimensions, this projection, or map, has everywhere a flat geometry. Locally, such a projection will hold. In their immediate vicinity, the space-time intervals an observer measures will always be accurate. But if they want to know what local space-time intervals observers who are located elsewhere will measure, they will need to supplement their space-time map with a metric. To formulate such a metric, the theory of differential geometry tells us that if we cut out a portion of a curved surface, so long as this portion is small enough to be considered flat, the only operations we need to worry about performing upon it in order to fit it to our map are the operations of stretching and/or skewing. Therefore, we can regard the local coordinates on a surface piece as being stretched and/or skewed relative to the map coordinates. Algebraically, this translates into an ability to express the surface coordinate intervals which we'll label dx prime and dy prime, as a linear combination of the map coordinate intervals dx and dy. Now, the local surface coordinates on our small, nearly flat patch of curved Earth correspond to its true geometry. So the true distance between these two locations is simply the Pythagorean relation dx prime squared plus dy prime squared. Substituting the map coordinate expressions of these intervals into the equation, then expanding out and collecting terms, we see that we get a new expression for the true surface distance, but now in terms of our map coordinates, dx and dy. This means we have successfully achieved what we set out to do at the beginning of this video. That is, describe the distance on a small portion of the Earth in terms of the coordinate lengths dx and dy on the map. We then array the coefficients of this expression into matrix form. These are the components of the metric tensor. Since one coefficient is counted twice, it is, strictly speaking, redundant, and so is termed symmetric. We also express the distance element formula via a more concise notation, which indicates the need to sum over the various infinitesimals and their corresponding coefficients. This notation can be used for any number of dimensions, which is handy because in a minute we're about to add a few. But first, we can give clearer geometric interpretation to the components of the metric tensor by noting that each term of the distance element formula corresponds to a length or angle value in the law of cosines expression. Visually, this makes sense because if instead of transforming a piece of the surface to fit to the map, we transform a piece of the map to fit to the surface, the right triangle formed by the map intervals dx by dy becomes an obtuse or acute triangle. This resizing means the length of the map intervals are stretched or shrunk by the square root of the value of the metric tensor's diagonal components, while the angle between the intervals is skewed by an amount determined via the off-diagonal component. We can therefore view the metric tensor in two distinct but equivalent ways. 1. As encoding a description of distance relative to a stretched and/or skewed grid. And 2. As a list of instructions for resizing an infinitesimal piece of a map in order to fit it to a surface. And both these views hold, even if our grid is a space and time grid, or our map one of space-time events. But in going from a physical manifold to the space-time manifold, we need to recognize a few things. First, that geographic locations become space-time events. This means that space-time coordinate intervals, instead of being defined by the span or vector between two geographic locations, are defined by the span or vector between two world events. Secondly, physical distance becomes space-time distance, meaning that our manifold invariant, instead of being defined by the distance a local surveyor would measure traveling between two geographic locations on the surface of the Earth, becomes defined by the space-time distance a local observer would measure traveling between two world events on the space-time manifold. Lastly, Euclidean angles in space become hyperbolic angles in space-time, Now, before you go panicking about having to learn hyperbolic trigonometry, we can note that the coordinative dx interval is defined by the span of two nearby world events which the map observer perceives as being simultaneous. But a local observer in that region may not perceive these two world events as being simultaneous. Similarly, the world events defining the span of the coordinative dt interval are perceived by the map observer as being only separated in time. However, a local observer may measure them as also having spatial separation. If either of these is the case, the local observer's spacetime grid may have to be skewed to fit to the map grid, or vice versa. Thus, for a simplified two-dimensional map of spacetime, the metric tensor would have three components. The first would indicate to us the true spacetime distance between the world events defining the span of the coordinative dt interval. The second would indicate the true spacetime distance between the world events defining the span of the coordinative dx interval. And the third would tell us whether or not these coordinate intervals would retain their Minkowskian orthogonality in a local frame. One of these spacetime lengths, once squared, would need to be made negative to reflect that the formula for spacetime distance is hyperbolic. Now, to go to higher dimensions, we need to add in the intervals dy and dz. Our two-dimensional flat map thus becomes a four-dimensional flat map. And we have to consider all the ways a four-dimensional infinitesimal hypervolume could be stretched and or skewed in order to be fitted to a new geometry. 4 dimensions to a hypervolume means 4 lengths that can be independently resized. We can also independently skew the angle between every pair of dimensions, meaning the angle between the t-axis and the x-axis can be skewed. The angle between the t-axis and the y-axis can be skewed, and so forth. 6 skewable angles plus 4 resizable lengths yields 10 total possible components. Arraying these in their proper matrix form, the 4 diagonal components will tell us, for any given infinitesimal piece of a spacetime observer's map, how to resize the 4 coordinate lengths dt, dx, dy, and dz, so that their new lengths correspond to the proper spacetime distance between the world events which define their span. Meanwhile, the 6 off-diagonal components will tell us how much to skew the 6 coordinate angles dt dx, dt dy, dt dz, dx dy, dx dz, and dy dz in order to match them to their proper spacetime values. These proper spacetime distances and angles are, of course, the ones that would be measured by observers local to the system there. Now, it's important to note that nowhere are the axes of space and time actually being skewed or stretched with respect to one another. Local observers on the manifold will always construct the 4 dimensions of space and time in a normalized orthogonal fashion. It's just that a non-local, distant observer may end up squashing and distorting this construction in order to fit it to their projection. Locally, time and space always look the same. But non-locally, time and space are only coordinative projections, mere grid lines drawn on a map. So at last, we have a fully geometric interpretation of the spacetime metric. And indeed, it's this geometric resizing of infinitesimal pieces that allows us, finally, to resolve the problem of determining the spacetime distance on a spacetime map. Given any two world events on a map, the coordinate path between them, and the metric for that map, the spacetime distance is easily calculated using the metric, plus some calculus. But that's only the beginning of the metric's real power, because analyzing how the metric changes from point to point on our map can tell us about the fundamental nature of our surface. But that's for future videos. This has been Dialect. Thanks for watching.